Welcome. This is exam 3 presented by Luis Urquieta Lopez. The objective of this presentation is to analyze the model of a mechanical system described by the following equation. Under the assumption that it is a frictionless system and the initial conditions are at equilibrium. First, we are going to find the transfer function. To do this, first simplify the function that we get at the beginning, and then use Laplace transform to get the frequency version of the function. Once you do that, you get the set input as u and output as y, and the output should be over the input, which will give you your transfer function that we call GS. Once we get the transfer function, we proceed to find the DC gain and natural frequency. Since we don't have a constant at the end of our denominator, we can factor out S and assume second behavior for our equation, which will help us get our M, B, and K values. After finding the values, just plug them in the formulas for DC gain and for natural frequency to get the following answers. Then we are going to find our final and initial steady state values of output using final value theorem and initial volume theorem. Using the formulas, just plug the your transfer function GS, find the limit according to the formula. And here we find the limit as S approaches to 0, which was your 1/5. Initial value theorem, you have to use it as S approaches to infinity, which gives you a 0. The step response is obtained using MATLAB and assuming second order behavior. From then, the rise time is obtained, the settling time, the overshoot, and the delay time. The overshoot is the highest peak here, and the delay time is the half time to get to steady state. 0.1. That's the time at that point. Then the body plot is obtained using the transfer function. And from there, the gain margin comes out as 14 decibels and the phase margin as 87.7 degrees. For more information about MATLAB, go to appendices. So far, we've been looking at the transfer function like an open loop. But if we consider this diagram of a closed loop feedback with a gain of k, we obtain the closed loop transfer function that will help us as we continue with the rest of the analysis. First, we find the root locus graph that will tell us our zeros and poles. In this case, we have 1 0 and 2 poles, which makes sense looking at our denominator for this transfer function. Since the S will give you the S out here will give you 0, and the function inside will give you 2 poles, most likely imaginary. For a closed loop transfer function, we can get our characteristic equation. That is just the denominator of the transfer function. From the characteristic equation, we can get the ratio of k and critical gain using Raoult's stability criterion. In this case, the range is 5 to 0, and the critical gain is 5. Using again our characteristic equation and turning S into JW, we can find our frequency, which then we can use to find our critical period. The critical period and the critical gain will help us to find our parameters for our PID and PI controllers. You can see here the critical gain. We can use the Ziegler-Nichols second method and find our KP value for our P control parameter. Also using the Ziegler-Nichols second method and the critical period and critical gain, we can find the parameters for the PI control parameter. And for the PID control, we use all all of the values before in the Ziegler-Snickers second method, and we found our 3 parameters for the PID control. Using the parameters previously mentioned, we can set up the P, PI, and PID controls in Simulink. That the end result will give you the step response graphs adjusted to the P, PI, and PID controls. From this, we can see that the P control is the one that gives you the less overshoot. So we're gonna pick this as our best for our purposes. Thanks for watching.